Nath, welcome to Mo Physics. So today we will start chapter number 26, that is direct current circuit. Okay. So now, first we will discuss what is Kirchhoff's law. What is Kirchhoff's law? So Kirchhoff's law define two law. One is KCL, that is Kirchhoff's current law. Sometimes it is called point law. Point law. Next is your KVL, that is Kirchhoff's voltage law. Kirchhoff's voltage law. So that is also called loop law. So now first we will discuss what is Kirchhoff's current law, KCL. Kirchhoff's current law. So what is Kirchhoff's current law? Suppose this is a point or junction. So there are so many branches are connected to this junction. Okay, so there are 5 resistors connected to this junction O or point O. So now let us say the current in this branch is I1, in this branch it is I2, in this branch it is I3, in this branch it is I4, and in this branch it is I5. Now according to KCL, the algebraical sum of current meeting at any point is equal to 0. So we can write the algebraic sum of current meeting at a point or junction is equal to 0. Algebraic sum of current meeting at a point or junction is equal to 0. So this is your KCL. So now you know current has a direction. Though it is a scalar quantity, I have already proved that current is a scalar quantity. So now you see, if incoming current is taken to be positive, then outgoing current is taken to be negative. So according to Kirchhoff's current law, the total algebraical sum of current at meeting at a point is equal to 0. So if I will say I1, so yes, you see I1 is incoming current, so I can take it is positive. And I3 is leaving current from this junction, I can say it is negative. So according to that sign, you write down the total sum of all the current. Here you see I1 is incoming current plus I2 is also incoming current plus, but this I3 is leaving current, that is minus I3 plus. Here I4 is incoming current, that is plus 4, then plus I4, and here I5 is leaving current, so it is minus I5. So according to KCL, it is equal to 0. Or you can say I1 plus I2 plus I4 is equal to, take this to right side, it is I3 plus I5. Then what is I1 plus I2 plus I4? It is nothing but total incoming current to the junction. And what is I3 plus I5? It is nothing but the total leaving current from this junction. So we can say total incoming current is equal to total outgoing current. Total incoming current is equal to total outgoing current. So this statement you can say it is also according to which law? KCL. So there are two definitions of KCL. Either you can write the total algebraical sum of current meeting at a point is equal to 0, or total incoming current is equal to total outgoing current. And you see, what is current? It is nothing but rate of flow of charge. So charge per unit time is called current. So we can say the total algebraical sum of current meeting at a point is 0 is nothing but total charge per unit time is equal to 0. Or you can say the total incoming charge per second is equal to total outgoing charge per second. So that indicates you can say the KCL obeys. KCL obeys which law? It is conservation of charge. Conservation of charge. So basing upon the conservation of charge, KCL is defined. Okay. So now let us take an example. Suppose this is a branch. So in this branch there is an ammeter. So this ammeter is A1. And this is another branch. Here the ammeter is taken to be I2. Here this is another branch of the circuit. So here ammeter A3 is connected. Now here you see this is another branch. So here ammeter A4 is connected. This is another junction. So there are two resistor connected here. Let us say this is A5 and this is another conductor which is connected to A5. So this is a circuit. Out of the total circuit, this is a part of circuit. Here, suppose in this case, this ammeter will read 6 ampere. And let us take the direction like this. And here, this ammeter reads say 2 ampere. And this direction of the current is like this. Okay. So here, this ammeter is reading what current? 3 ampere. And this A5 ammeter is say it is showing let us say this A5. Okay, this is A5. You can say this is A6. So in this ammeter, that is A5, shows 1 ampere current. Then the question is, what is the reading of this ammeter A2? What is the reading of ammeter A6? Okay, this is the question. Now see, in this junction, the 6 ampere and 2 ampere are coming to this junction. And here there are two branches. So here there are two branches. In this branch, the current is leaving. Let us say this is the direction of the current. So here current leaving is how much? 3 ampere. Then what is the current read by this ammeter A2? So now you put the put the KCL to this junction. So what is KCL? The total incoming current must be equal to total outgoing current. So here the total incoming current, let us say this is junction number O1, this is junction number O2. So at junction O1, the total incoming current is nothing but 6 ampere plus 2 ampere. 6 ampere plus 2 ampere. And here, what is the current leaving from this junction? This is 3 plus. I don't know what is the direction of the current in this case. So let us say the current through this ammeter is equal to I2. So now from this we can say 8 is equal to 3 plus I2. So that implied I2 is equal to 8 minus 3, that is 5 ampere. And it is coming what? It is 6 plus 2, 8. And here it is leaving 3. So you see it is coming 5 ampere. That means this 5 ampere, we have taken this I2 according to leaving current. So I2 is coming 5 ampere. That means the current through this ammeter will be 5 ampere. So this is the answer. So this ammeter will read what? 5 ampere. Now at junction number O2, you see the 3 ampere is incoming, 1 ampere is also incoming. And there is another branch, this. So we know as per the KCL, total incoming current is equal to total outgoing current. Here incoming current is 3 plus 1. So definitely this incoming current must pass through this ammeter. So that means the current, let us say this is I6. So I6 is equal to 4 ampere. So that means the direction of this current through this ammeter is equal to outward from this junction. Let us say this is 6 ampere. So this is the solution of Kirchhoff's current law. I think it is clear. Now the second law is your KVL, Kirchhoff's voltage law. So what is this? Kirchhoff's voltage law. So according to the Kirchhoff's voltage law, it is applicable for a closed circuit. Let us say you take an example of, you take the source, that is E1, another source is your E2. Okay, and these E1 and E2 are connected to two resistance. Let us say this is R1, this is R2. So now according to Kirchhoff's voltage law, which is applied to a closed circuit, so according to the KVL, the algebraical sum of total EMF is equal to algebraical sum of IR drop in a circuit. So you can write here the algebraic sum of EMFs is equal to the total algebraic sum of IR drop. What is IR drop? I into R is nothing voltage. So the total supplied EMF is equal to total voltage drop in the circuit. Okay. So here, in the latter part, I will give the proper sign. So you now remember here the two batteries, two cells are connected in same sense. That means here the two voltage, that is E1 and E2, are additive. So total EMF in this circuit is equal to E1 plus E2. Let us say the current passing through this circuit is I. So here it is series circuit, current remains same. So what is the voltage drop across R1? That is I into R1. And what is the voltage drop across R2? That is I into R2. So this is your, according to which law? Kirchhoff's voltage law. So algebraical sum of EMF is equal to the total voltage drop across the resistive circuit. Just an example, suppose you see in a family, father is drawing salary and son is also drawing salary. The total salary is nothing but total EMF, and which is equal to total drop. Drop means you are going to restaurant, you are going to buy any ornament. So in that your salary, your money will drop. So that's why this is just example. So this is your KVL, and you know KVL obeys which law? KVL obeys the conservation of energy. Conservation of energy. Because you know energy is equal to power into time, power is equal to V into I. So power is equal to V into I in a circuit, in a closed circuit. So you can say the total energy supplied by the EMF is equal to total energy drop in the resistors. So this KVL obeys the law of conservation of energy. I think it is clear. So next, what is the example? What is the example of DC circuit? Example of DC circuit. So you have marked in your mobile there is flashlight. So that flashlight circuit, the flashlight circuit is example of DC circuit. And you have marked in your bike or scooter or in a car, there is various wiring system. Okay, there is indicator circuit, there is brake circuit, so there is a headlight circuit, all the circuit in automobile is example of DC circuit. Then what is the example of AC circuit? Example of AC circuit. In our household, electrical appliances, electrical circuit is the example of AC circuit. Here the source of EMF is alternating current. Okay, but here in DC circuit the source of energy is your battery or solar cell, like that. So this is the example of DC circuit and example of AC circuit. So now we will start the combination of resistors. So combination of resistors, there are two types of combination. One is called series combination, another is called parallel combination. So first we will discuss what is series circuit, series combination. So now see, so there are n number of resistors I have taken. In any resistor there are two ends. Okay. So now you see the first end of this resistor is connected to the voltage source. The second of the resistor is connected to the first end of the second resistor. And the second terminal of the second resistor is connected to the first end of the third resistor. In this way, we can connect in series. So here what happens? The current will start from the positive terminal. So here what is the current? Current is I. Here also what is the current? I. So here also I. That means since there is only one path, current will remain same. So this is the characteristic of series circuit. In series circuit, current through each resistor remains same. So current through each resistor remains same. So now we will apply KVL, Kirchhoff's voltage law. Now you see, when current passes through any resistor, there is a voltage drop. Suppose current passing through this R1 resistor is I, resistance is R1. So what is the voltage drop across this R1? That is V1. So V1 is nothing but I into R1. So here voltage drop across this resistor is V1. Here voltage drop is V2. Here voltage drop is V3. Here voltage drop is Vn. And we have already read the KVL. So as per KVL, Kirchhoff's voltage law, the total algebraical sum of EMF, there is only one source, that is V. This is the EMF, which is nothing but total voltage drop across all the resistors. So here that implied V is equal to, what is V1? It is nothing but I into R1. What is V2? It is I into R2. Similarly, what is voltage drop across nth resistor? That is I into Rn. So that is equal to I, take common I, it is R1 plus R2 plus Rn. So this is your V. This is your V. But what is equivalent resistor? Equivalent resistance means, suppose you see, this is your A terminal, this is your B terminal. Instead of, so there are n number of resistors connected in the series. So what I will do, I will take same point A and same point B. Here, instead of n resistor, I will connect a single resistor. Let us say its name is RS. So total resistance in series circuit. So in place of n number of resistors, I have taken a single resistor across the same terminal with the same voltage source. I am not changing the voltage source. What is the EMF of this cell or battery? It is V. So here the n number of resistors, we are drawing I current. Here single resistor is also drawing I current. Okay, so now see, this circuit is equivalent to this circuit because instead of n number of resistor, I have taken single resistor, and that single resistor is also drawing same current from the same source like this. So here this RS is called equivalent resistance of R1, R2 up to Rn. So now see, in this circuit, what is the voltage across this resistor? The V. You see, this positive terminal is connected to A point. If that this voltage is V, this negative terminal is connected to this point. This voltage is 0. So here the voltage difference, potential difference across this resistor is V minus 0. That is V. And you know, according to Ohm's law, I is equal to V by Rs. I is equal to V by Rs. Or you can say V is equal to I into Rs. Now in this V, you put I into Rs, which is equal to I into R1, R2 up to Rn. So I cancel. So we got Rs is equal to R1 plus R2 plus Rn. So this Rs, what is this Rs? So this Rs is called equivalent resistance in which connection? In series connection. So this S stands for series connection. So this is the equivalent resistance formula in series circuit. So you have marked, I have discussed the capacitors. So in capacitors, the parallel connection, we had got the equivalent capacitance is equal to C1 plus C2 up to Cn. That is in parallel case. But same type of equation you will get in series in case of resistors. So what will happen in this series connection? What will happen? You see, suppose I will take two resistors connected in series. One resistor is 6 ohm, another resistor is 3 ohm. Then what is the equivalent resistance? It is nothing but 6 plus 3, which is equal to 9 ohm. So this 9 ohm is greater than the highest of individual. Here 3 ohm, 6 ohm. Which is highest value? 6 ohm. But we are getting net resistance is greater than 6 ohm. Or we can say the equivalent resistance in series connection is greater than the highest of individual value. Highest of individual value. That implied in series connection net resistance increases. So when we will suppose in the market there is 6 ohm and 3 ohm are available. But when you will do a project, you need 9 ohm. So this 9 ohm is directly not available in the market. So what you will do? You just connect the 6 ohm and 3 ohm in series so that you will get the your desired value, that is 9 ohm. Okay. So what is the example? What is the example of series circuit? What is the example of series circuit? Now you see, in marriage function or any other function, you have marked there is various small balls connected in series. So that string of balls are which circuit? Series circuit. Suppose you are connecting very low voltage ball. Suppose each ball rating is 1 volt and you have connected 100 volt. So if I will connect that 1 volt bulb across this 100 volt, so bulb will burst. The bulb will fuse. So in that case, if you will connect 100 bulbs in series, then each bulb voltage will be 1 volt, 1 volt, 1 volt like that. That means voltage will be divided across each resistor in the series circuit. Okay, so this is the example of the string of balls are connected in which circuit? Series circuit. I think it is clear. Now, why, if anybody will ask, what is the concept of series circuit? Why resistance increases? You see, I have already discussed what is the formula for R. R is equal to rho divided by rho into L by A. Okay, length by area of cross section into specific resistivity is equal to R. Now you see, when you are connecting these two resistors in series, if you are connecting these two resistors in series, what will happen? The length of the conductor will increase. If length of the conductor will increase, keeping area same, then resistance will increase. This is the fundamental concept. Okay. So now let's discuss how the voltage is distributed among all the resistors connected in series. Voltage distribution in which circuit? In series circuit. So how the voltage is divided? Okay. So now you see. So there are, let us say, there are n number of resistors connected in series to a voltage source V. So this is R1, this is R2, this is Rn. So here what happens? The current remains same in each resistor. And what is the equivalent circuit? Equivalent circuit is equal to what is the total resistance? Total resistance is Rs. That is connected to the same voltage source V, and it is drawing same current as that of the previous. Now, what is the value of I? I is nothing but V by Rs. Okay. Then same I will pass through R1. Then what is V1? V1 is nothing but V by Rs into R1. What is V2? V2 is equal to I into R2. I is nothing but V by Rs into R2. So that means in every case V by Rs is same, which is nothing but current. So how the voltage depends upon resistance? So voltage is directly proportional to the resistance. So we can say voltage is directly proportional to the resistance. If in the series circuit resistance value is more, then voltage across that resistance is also more. Just take an example. You see, let us say this is 6 ohm, this is 3 ohm. It is connected to a battery of 18 volt. So here what is the current? I is equal to E by R1 plus R2, 6 plus 3, that is equal to 2 ampere. Then what is the voltage across 6 ohm? Let us say this is V1, this is V2. So voltage across 6 ohm is equal to I into resistance of 6 ohm. that is equal to I is 2. Resistance of this 6 ohm is 6, that is 12 volt. Then what is the voltage across this 3 ohm resistor? It is nothing but I into resistance of second resistor, that is I is equal to 2, resistance is equal to 3, that is 6 volt. Okay, now you see, across the 6 ohm resistor you are getting more voltage, 12 volt. Across the low resistance, that is 3 ohm, you are getting less voltage. So this calculation is whether correct or not, you have to prove by which law? KVL. So what is KVL? Total incoming voltage, or you can say total supplied EMF is equal to 18 volt. And that must be equal to the sum of voltage drop across these two resistors. So here we are observing the voltage across 6 ohm is 12, here it is 6, so 12 plus 6 is equal to 18. So this is the cross checking whether you have done right or not. Okay, so this is about the series circuit. Now parallel combination of resistors. You see, suppose the resistance value is here R1, here R2, we have taken n number of resistance, here resistance is Rn. So how they will be connected in parallel? You see, the first end of all the resistors are connected to a single point, and the second end of all the resistors are connected to another single point. And let us say this point is connected to A terminal, this point is connected to B terminal. Okay, so now see, if the potential across this positive terminal is V, the potential at negative terminal is 0, then what is the potential difference across the terminal? V minus 0. So now this point and this point are same potential because there is no other resistor or any electrical device are connected in between this point and this point. So if the point is A, so this point we can say it is A, the same potential. So what is the potential of A point? V. So here potential is V. And here this 0 terminal, the negative terminal of the battery is connected to B point as well as this point. So this point is also called B, where voltage is equal to 0. So now you see this R1 is connected across A point, B point. Then what is the potential difference across R1? V minus 0. That is here the potential difference is V. And what is the potential difference across this R2? The first end is connected to here, second end is connected to 0 potential, then again the potential difference is V. Similarly, potential difference across Rn is equal to V. So we can say in parallel circuit, what remains same? The potential difference across each resistor remains same. This is the characteristic of parallel connection. But what will be the difference? You see, so here let us say current is incoming from the positive terminal of the battery is I. So this I current will be divided along various branches according to which law? KCL. Let us say current is I1 here, current is equal to I2 here, current is equal to IN. So now as per Kirchhoff's current law, we can say total incoming current to this junction A is equal to total outgoing current from the junction. So that is equal to I1 plus I2 plus I3 plus up to IN. Now what is I1? So I1 is current through this resistor R1. What is the potential difference across R1? It is V. So I can write I1 is equal to V by R1. Similarly, I2 is equal to potential difference across R2 is equal to V. Resistance is R2. Just apply simple Ohm's law. So I2 is equal to V by R2. In this way, what is the current in nth resistor? It is V by Rn. So that is equal to V common 1 by R1, 1 by R2 plus up to 1 by Rn. So this is the current through this circuit. Now what I will do, instead of n number of resistor, I will connect a single resistor. I will replace, I will remove all the resistor across A and B terminal. This is A and this is B part. So in place of n resistor, I will connect a single resistor whose resistance value say Rp. And these A and B are connected to the voltage source whose potential difference is V. Here I am also taking same voltage source V. Here all the N resistor were drawing I current. Here this single resistor is also drawing I current. So current will flow like this. So this is the equivalent circuit of this circuit. Okay. So here what is the potential difference across this RP resistor? So here you see this terminal is connected to A, this terminal is connected to B. If the potential difference across this terminal is V, then the potential difference across A and B is also V. Then what is I? I is nothing but V by resistance. What is the resistance? RP. So in place of this I, I will write V by Rp, which is equal to V into 1 by R1, 1 by R2, up to 1 by Rn. So V cancel. So what we got? We got 1 by Rp is equal to 1 by R1, 1 by R2, up to 1 by Rn. So this is the equation in case of parallel combination. So what is Rp? So this Rp is nothing but equivalent resistance of this n number of resistors which are connected in parallel. So equivalent resistance in which circuit? Parallel circuit. Equivalent resistance in parallel circuit. So if you have remembered in capacitor, we have got 1 by Cp is equal to 1 by C1 plus 1 by C2 plus 1 by Cn. So that is for which combination? For series combination. So the equivalent resistance in parallel is same as equivalent capacitance in which connection? Series connection. Okay. So now let us take, you see, suppose this is R1. This is R2. Both are connected in parallel. So what is the equivalent resistance? Equivalent resistance, I am writing it is Rp is equal to 1 by R1 plus 1 by R2. So that implied LCM is R1 R2, that is R2 plus R1 is equal to 1 by Rp. So that implied Rp is equal to R1 R2 by R1 plus R2. You can remember this formula because when there are two resistors are connected in parallel, directly you put this formula. Okay. So let us take an example. Let us say this is 6 ohm, this is 3 ohm, both are connected in parallel. Then what is the equivalent resistance? Equivalent resistance is equal to R1 into R2 by R1 plus R2. That is 18 by 9. That is 2 ohm. So what is the observation? What is the observation? You see. So here 2 ohm, the equivalent resistance 2 ohm is less than the lowest of individual. So lowest of individual out of 6 and 3, the lowest is 3 ohm, but we are getting the net resistance is less than the 3 ohm. So that means in parallel connection, the net resistance increases. In a parallel connection, the net resistance increases. If net resistance increases with the same voltage source, the what is current? Current is equal to V by Rp. So current carrying capacity increases. So this is the characteristic in parallel connection. In parallel connection, the total resistance decreases by which the current carrying capacity increases. So that is why we are using all the household appliances just like electric bulb, tube light, fridge, AC. Oh, we are using in which circuit? We are using the household appliances. Household appliances in which circuit? In parallel circuit, so that the current carrying capacity will increase. Similarly, suppose there are three resistors. There are three resistors connected in parallel. This is R1, R2, R3. Then what is the equivalent resistance? So 1 by Rp is equal to 1 by R1, 1 by R2, 1 by R3. So just take LCM R1, R2, R3. So that is equal to, if you divide R1, it is R2, R3 plus R1, R3 plus R1, R2. So that implied the equivalent resistance in parallel in case of these three resistors, it is R1, R2, R3 divided by R1, R2 plus R2, R3, R3, R1. So don't try to remember this formula. You can directly put this. Okay, if there are three or more resistors connected in parallel, you can directly put this value. Now question comes in parallel connection. In parallel connection, why resistance decreases? From basic concept, we have to justify in parallel connection why resistance decreases. By the formula we got, but why resistance decreases? Now you see, suppose this is a resistor R1, this is another resistance R2. If we'll add this, if we'll connect in parallel, so what will happen? The net, so here let us say the area of cross section is A1. Here area of cross section is A2. When both are connected in parallel, the net area will be A1 plus A2. So the net area of this total two conductors will increase. So the area of cross section will increase. But length remaining same. Here length L, here length L. So L length is same, but area of cross section increases. So as per the formula, R is equal to rho L by A. So here rho is constant, L is constant for every resistor. But if both are connected in parallel, area of cross section increase. If area of cross section will increase, then net resistance will decrease. So this is the case. This is the fundamental concept why in parallel connection resistance decreases. Another thing is that suppose you take two identical resistors R and R, both are connected in parallel. Then what is the equivalent resistance? It is 1 by R plus 1 by R, that is 2 by R. So from this we can say the equivalent resistance in the parallel is equal to what? R by 2. So if two identical resistors are connected in parallel, the equivalent resistance will be half of the individual. Similarly, if we connect three identical resistors, same value, that is R, 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 both are connected in parallel, then what is the equivalent resistance? It is nothing but R by 3. Okay. Similarly, if there are n number of resistors, n number of identical resistors are connected in parallel, then what is the equivalent resistance? It is the resistance of individual value divided by n. So in this parallel combination, net resistance decreases. Now see, current division in parallel circuit. Suppose there are two resistors R1 and R2 connected in parallel. The total incoming current to this combination is I. Out of I1 will flow through R1 and I2 will flow through R2. And definitely as per KCL, we can say I is equal to I1 plus I2. Okay. So now let us say this point is A, this point is B. If I1 passes through this R1, then what is the voltage drop across this R1? I1 into R1. So I1 into R1 is the voltage potential difference across this. And here what is the potential difference across this R2? So current is I2 and resistance is R2. And since both are connected in parallel, the potential difference across 2 will be same. Or we can say I2 is equal to I1 R1 divided by R2. Okay. So from this equation, I is equal to what? I1 plus I2. In place of I2, you write down I1 R1 by R2. Take common I1. So if you take common I1, LCM is R2. So it is R2 plus R1 divided by R2. So from this we got I1 is equal to I into R2 divided by R1 plus R2. And what is then what is I2? Then what is I2? I2 is nothing but I1 R1 divided by R2. So I1 we have got I into R2 by R1 plus R2 into R1 divided by R2. R2 cancel. So we got I2 is equal to total current I into R1 by R1 plus R2. So this is the current division formula. This is the current division formula. You see, I1 is equal to I into R2. That means when you will calculate the current to the first branch resistor, what you will do? So I1 is equal to total current I into opposite side resistance R2 divided by R1 plus R2. Similarly, the current through the second branch I2 is equal to total current I into opposite side resistance R1 divided by R1 plus R2. Okay, or we can say the total current I1. So I1 by I2. What is I1? It is V by R1. What is I2? V by R2. So that implied I1 is to I2 is equal to 1 by R1 is to 1 by R2. That is, current divides in parallel circuit by inverse ratio of their resistance. Inverse ratio of their resistance. So let us take a solution. Let us take an example. Suppose you see, this is your 6 ohm. This is 3 ohm. The total incoming current I is equal to 18 ampere. So here current is I1, here current is I2. Then according to this formula, current division formula, so what is I1? I1 is nothing but I is nothing but 18 into R2. That is, that when you will find the current to first branch, you have to take the total current into opposite side resistance, that is 3 by 3 plus 6. So which is equal to 6 ampere. Then what is current through the second branch? I2. It is total current 18 into opposite side resistance, that is 6 by 3 plus 6. That is equal to 12 ampere. You see, the current in 3 ohm resistor is 12. Current in 6 ohm resistor, it is 6 ampere. Okay, and if we apply KCL, the incoming current is 18, the outgoing current is 6 plus 12, that is 18. So current divides in inverse proportion of the resistance. If resistance is less, current will be more. In this way, so how will you find, according to this formula, how will you solve this problem? You see, so I1 is to I2 is equal to what? 1 by R1. R1 is 6 ohm is to 1 by R2. R2 is 3 ohm. So just multiply here 6 and 3. You multiply 6 in numerator. So that is 6 by 6. 6 by 6 is to 6 by 3. That is equal to 1 is to 2. That means in I1, if current is X, in I2, the current will be 2X. Now how will you find the I1? I1 is equal to, it is sharing percentage 1 out of 1 plus 2 into total current. Total current is how much? 18. So that is equal to 1 by 3 into 18, that is 6 ampere. Then what is I2? I2 share is 2 part. 2 part of total 1 plus 2 into total current 8. That is 12 ampere. In this way also, you can solve this problem. Okay. Now see, in this example, there are 3 resistors connected in parallel, and the total current coming to this junction is 44 ampere. So you have to find what is the current through the individual resistors. So definitely the total current coming to this junction 44 must be equal to I1 plus I2 plus I3. Okay. So how will you solve this problem? and I have told the current divides with inverse proportion of the resistance. That means here I1 is to I2 is to I3 is equal to 1 by R1 is to 1 by R2, that is 4 ohm, is to 1 by R3, that is 6 ohm. Okay, so here the LCM of 2, 4, 6 is equal to 12. Is equal to 12. So multiply in each fraction 12 by 2 is to 12 by 4 is to 12 by. So this is just mathematics. In the school career you have read like this. So that is equal to 12 by 2 is 6 is to 3 is to 2. So this is your I1 is to I2 is to I3. Now I want to find I1. So I1 is what part of the total fraction, that is 6. So 6 divided by 6 plus 3 plus 2 into total current. Total current is equal to 44. So that is equal to 6 by 6, 3, 9 plus 2, 11. 11 into 44. So that is I1 is equal to 24 ampere. I1 is equal to 24 ampere. Similarly, what is I2? I2, what is the total part of the, what is the sharing of I2? That is 3. So 3 divided by total. Total is 6 plus 3 plus 2 into total current. Total current is equal to 44. Calculate this. So it is 12 ampere. Then what is I3? I3 is equal to 2 by 6 plus 3 plus 2 whole into total current, that is 44. So that is equal to 8 ampere. So how will you cross check whether your answer is correct or not? The 44 ampere must be equal to I1 plus I2 plus I3. So here I1 is equal to what? 24. I2 is equal to 12. I3 is equal to 8. So just you add this, so you will get 44 ampere. So this is the for cross checking. Suppose you have forgot this formula. Okay, you have forgot this formula. Then how can you solve in another way? So you see, if your concept is clear, you can solve this problem in another way. You see, you find out what is the equivalent resistance of these 3 resistors. So you see, this is your A point, this is your B point, and instead of these 2, 4, 6 which are connected in parallel, I will connect a single resistor. I will connect a single resistor whose resistance value is Rp. And what is the total current coming to this junction? 44 ampere. Now we have to find what is Rp, equivalent resistance of these 3. Then I have to find what is the voltage across A and B. So how will you find Rp? So 1 by Rp is equal to 1 by R1, 1 by R2, 1 by R3. So what is the LCM? LCM is 12. 12 to the 6 plus 3 plus 2, that is 11 by 12 is equal to 1 by Rp. So that implied Rp is equal to 12 by 11. Rp is equal to 12 by 11 ohm. So here Rp is, we got 12 by 11 ohm. Then what is the voltage across A and B? Voltage across A and B is nothing but I into Rp. So I is 44, Rp is 12 by 11, so that is equal to 48 volt. So since voltage across A and B is 48 volt, so voltage across 2 ohm is also 48, voltage across 4 ohm is also 48, voltage across 6 ohm is also 48, because potential difference remains same across each resistor in parallel connection. So I can write what is I1. I1 is the voltage across this, that is equal to 48 volt divided by R1. R1 is equal to 2 ohm, so which is equal to 24 ampere. So this is your I1. Similarly, what is I2? I2 is the voltage across this, that is 48 volt divided by this resistance 4, so that is equal to 12 ampere. Similarly, what is I3? I3 is equal to voltage across this, that is 48 divided by 6, that is 8. So answer is correct. Here I1 24, here I1 24. I2 is equal to 12 ampere, here 12 ampere. I3 is equal to 8 ampere, here I3 is equal to 8 ampere. You take, you see, So there are n number of identical resistors of R value each are connected to a voltage source of V. And same resistors, that is same identical resistance R up to how many times? N times. All are connected in parallel with the same voltage source. Then we have to compare in both cases, in series and in parallel, we will calculate what is the power consumed by this resistor and we will compare what is the relationship. Okay. Now you see, so in this case, in series, what is the equivalent resistance? Equivalent resistance is nothing but R plus R1 plus R2 plus up to how many times? N times. That is equal to N into R is the equivalent resistance in series connection. Then what is the power consumed by all the resistance in series connection? Power is nothing but V square by R. This is the general formula. So here voltage is V and what is the total resistance of the series combination? RS. So that is equal to V square by RS is nothing but NR. So this is your equation number 1, that is power consumed in which circuit? Series circuit. Now come to power consumed in parallel circuit. So in parallel what will happen? All the identical resistance are connected in parallel. Then how many times of resistors? N times. Then what is the equivalent resistance? I have already told. The equivalent resistance is equal to R by N. And the total resistance, that is equivalent resistance R by N, is connected across this source whose potential difference is V. Then what is the power in case of parallel combination? Power is nothing but V square by resistance. So here resistance is nothing but Rp, that is equal to V square by Rp. Rp is equal to what? R by N. So that implied power consumed in parallel circuit is equal to, you take N to numerator, N into V square by R. Okay. So just multiply N in numerator as well as denominator. If you multiply N in numerator, it is N square V square by the divide also N, so NR. So that is equal to N square. But what is V square by NR? V square by NR is nothing but power consumed in series circuit. Power consumed in series circuit. So we got a formula, power consumed in parallel circuit is N square times power consumed in series circuit. So that means in case of parallel, the power consumed by the load is more. If power consumed by the load will be more, so that power can be delivered by the load. That means all the resistors, all the electrical appliances, when connected in parallel, they will give their performance better than that of series. Okay. So this is the relationship. Just take an example. Let 3 resistors, identical resistors, okay, 3 resistors, that is identical resistors, are connected in series, and they consumed, all the resistors consumed what power? 30 watt power. So if they are connected in parallel instead of series, if they are connected in parallel instead of series, they will consume what? Just you see that this is the formula. So power consumed in parallel circuit is N square times power consumed in series circuit. N means number of identical resistors. So here N is 3. So 3 the square into the total power, that is in series 30. So that is equal to 270 watt. So that is why all the electrical appliances are connected in parallel, so that they will give their performance better than that of series. In series, all the load consumes 30 watt in case of 3. But in parallel, you see the more consumption of the power. More consumption of the power by the load means they will deliver their performance with same power, that is 270 watt. So let us solve example 26.2. Two balls of resistance 2 ohm each are connected to ideal source of EMF 8 volt. First you have to find the current across each bulb and potential difference across each bulb and power delivered to the each bulb and to the entire circuit when both are connected in series and parallel. So first we will see series connection. In series connection, what is the net resistance, equivalent resistance, that is R1 plus R2, that is 4 ohm. Then what is the, in series connection, what is the current? The supply voltage is 8 volt, total resistance is 4 ohm, so that is equal to current is equal to 2 ampere. So current through this bulb is 2 ampere, current through this bulb is also 2 ampere, both are connected in series. Then what is the potential difference across each bulb? So I can say V1 is equal to I into R1. I is equal to 2, R1 is equal to 2, that is 4 volt. Then what is the voltage across second bulb? Second bulb, I is equal to 2 ampere, resistance is equal to 2, that is 4 volt. So you had given 8 volt supply to the both, so voltage will be divided equally because they are same resistance. So next, what is the power consumed by each bulb? So power P1 is equal to, you can put V1 into I1. That is V1, voltage across this is equal to what? 4 volt. And what is the current? Current is nothing but 2. So that is 8 watt. So this is also equal to power consumed by the second bulb. Both are consuming same power. Then what is the net power in series connection? Net power in series connection. So net power delivered to the bulb is equal to P1 plus P2, that is equal to 8 plus 8, that is 16 watt. So this is the power delivered to the entire circuit. Okay, come to second bit. You see, the two bulbs are now connected in parallel across the same voltage source, that is 8 volt. So here 2 ohm, here 2 ohm. So the total current is I. So here current is I1, here current is I2. So now we have to find what is the value of I1. So I1 is nothing but voltage across this divided by 2. Since both are connected in parallel and the potential difference across each end is the same as the supply voltage, that is 8. So I1 is equal to 8 by 2, V by R is equal to 4 ampere. So I2 is equal to same 8 volt by 2, that is 4 ampere. So here current drawn in the series circuit, you see current drawn by the two bulbs was 2 ampere. Now current carrying capacity of both bulbs increases by connecting in parallel. So this is the current through each bulb. Then what is the potential difference across each bulb? Since both bulbs are connected in parallel, the potential difference across both are same, that is V1 is equal to V2, and both are connected to the same source 8 volt. So V1 is equal to V2 is equal to 8 volt. Now see, compare. In series circuit, voltage across each bulb was 4 volt, but here voltage increases to 8 volt. So voltage increases, current increases, definitely power will be increased. So now we can say what is the power delivered to first bulb. Power delivered to first bulb is equal to V1 into I1. V1 is equal to 8 volt. I1 is equal to 4 ampere, 32 watt. Then what is power delivered to the second bulb? V2, I2. V2 is equal to 8, I2 is equal to 4, 32 watt. Then what is the total power? Total power must be equal to P1 plus P2. Now you see, how will you find the total power? So what is the total current drawn from the source? Total current drawn from the source is equal to say I. And what is the total supplied voltage? That is your V. So total power is equal to V into I. So V is equal to 8 volt into total current I is nothing but I1 plus I2. That is I1 plus I2. That is 4 plus 4. That is 8 into 8, 64 watt. And you see, you just cross check. The total power should be equal to P1 plus P2. So here P1 is 32, P2 is 32. So if you sum this, you will get 64 watt. And here you see power connected, power delivered in case of parallel connection is equal to 64 watt. And total power delivered in the series circuit, net power delivered in series circuit is equal to 16 watt. So what is the ratio? So ratio is power connected in the power parallel and power delivered in the series is equal to 64 by 16, that is equal to 4, which is nothing but 2 square. That means two identical resistors. So we have derived in the last part the power delivered in parallel circuit must be equal to n square power delivered in the series circuit if both resistance are identical. So here there are two resistance, identical resistance. So n square must be equal to 2 square. So that is power consumed in P is equal to n square. N is 2 square. Power delivered in series circuit is 16. So which is equal to 64 watt. It is also proved. Okay. Next question. If one bulb get fused, what happens to bulbs when in series? You see, if one bulb will be fused in series circuit, one bulb fused means this tungsten filament, the filament wire will be broken. That means this point to this point, this will be open circuit. This will be open circuit. If it is open circuit, resistance is infinite. That means no current will pass through this path. That means second bulb will also not glow. Okay. So in series case, if one bulb is fused, what will happen? So both bulbs will not glow. This is the answer. And what happens in the parallel? Suppose this bulb is fused. If it is fused, so this will be open circuit. That means resistance is infinite. So here what is the current? Current drawn by the first bulb will be 0. But in the second bulb, the voltage across the second bulb is still 8 volt. Then what is the current in the second bulb? I2 is equal to V8 by resistance, that is equal to 4 ampere. But what is I1? I1 is equal to 0. Okay. Now you see the first bulb will be fused. No current will pass through the first bulb, but second bulb will draw same current as that of the previous case. And what is the power delivered to the second bulb? Power delivered to the second bulb is equal to V into I. V is equal to 8 volt. I is equal to 4 ampere, that is 32 watt. But P1 is equal to 0. So that means second bulb will glow brighter as comparing to the previous case when the first bulb was not fused. So this is very interesting question we have solved now. So I think this is the last question of this video. Test your understanding 26.1. So there are four circuit A, B, C, D. All the resistors are identical of resistance value is R. So you have to find the equivalent resistance in this four circuit, and you have to rank the equivalent resistance from highest to lowest value. So first we will see first figure. So in the first figure, the equivalent resistance is equal to all the resistors are connected in a series. So R plus R plus R, that is 3R. Then come to in parallel connection in case of B circuit, that is the equivalent resistance in B circuit is equal to, since all the identical resistance, there are 3 resistors, the equivalent resistance will be R by 3. Similarly, come to C bit. So in C, what is the equivalent resistance? What is the equivalent resistance across the terminal? So here you see, these are connected in parallel. So let us see the RC. How will get the RC? So here this resistance is R, and in between this point to this point, the two resistors are connected in parallel. So R and R, what is the equivalent resistance? R by 2. So this R and this R by 2 are connected in series. So net resistance is R plus R by 2, that is 3R by 2. 3R by 2 is nothing but 1.5 R. And this R by 3 is nothing but 0.33 R. So now come to figure D. In figure D, what is the equivalent resistance? RD. So here these are connected in series. Then what is the equivalent resistance? 2R. And here this resistance is R. So we have to find equivalent resistance. So this is 2R, this is R. Then what is the equivalent resistance? So RD is equal to R1 into R2 by R1 plus R2. That is 2R into R divided by 2R plus R. That is 2R square by 2R plus R, 3R. That is equal to 2 by 3 into R. 2 by 3 is nothing but 0.67. I think, yes, 1 by 3. Okay. So 0.67 R. So now we have to rank the resistance value from highest to lowest value. You see, this is RA, this is RB, this is RC, this is RD. So which is highest value? In A. So I can write RA is greater than. Second is this 1.5. That is RC. Then it is RD. Last is RB. So this is the equivalent resistance. So with this I am concluding the today's lecture. So in the next class we will proceed.